You know when you watch like an Iron Man movie?
Oh, yeah, the classic lab scenes.
Right. Tony Stark is just waving his hands around, and these perfect, glowing 3D holographic models are just floating in the air.
It is the ultimate sci-fi dream.
Exactly, or the holodeck in Star Trek. We just kind of assume that one day, light will seamlessly zap out of our computers and create these perfect interactive worlds right in front of our eyes.
Which is a lot harder than Hollywood makes it look.
A lot harder. Because right now, the device you are listening to this deep dive on is doing billions of calculations a second. And if you look at the whole internet infrastructure making this stream possible, we are passing unimaginable amounts of data using light.
Right, photonics.
Yeah, photonics. Light is just racing around inside our fiber optic cables and inside our microchips at staggering speeds. And obviously, light is everywhere in the free space physical world you and I are sitting in right now.
But there is a huge catch.
There is. Here is a really strange counterintuitive fact. The moment you try to get that highly controlled digital light to leave the microscopic, flat world of a computer chip.
And enter the physical 3D room with you.
Exactly. The physics just entirely fall apart. It is one of the most frustrating roadblocks in modern science. So, welcome to the Deep Dive Lab. Today we are exploring a massive scientific mystery. We are taking a single source, a fascinating new research paper, to explore the physical boundary between digital chips and the real world.
And how a team of engineers just figured out how to finally bridge it.
Okay, let's unpack this. Why is it so incredibly difficult to get a perfect high-speed beam of light to jump off a microscopic chip?
Well, to understand the roadblock, we really have to look at the environment the light is leaving. Inside a photonic chip, light travels in what physicists call guided wave modes.
Guided wave modes.
Think of them as microscopic silicon tunnels. The light is trapped. It has a strict path, kind of like a bullet train on a track.
Makes sense.
But the moment that tunnel ends at the edge of the chip, the light enters free space. It is no longer constrained. And light, being a wave, naturally wants to diffract.
Right, it spreads out.
Exactly. It immediately spreads out like water bursting out of a hose. If you want a tight, perfect beam, like a laser pointer or a pixel in a hologram, you have to capture that spreading light and focus it.
Which usually means sticking a piece of glass, like a lens or a mirror, right in front of the chip.
Which creates a massive engineering headache known as the chip-to-world interface. For the longest time, engineers were trapped by a fundamental physical trade-off. They essentially had two bad options.
Just two?
Yeah. Option A was to use photonic integrated circuits, or PICs. These rely on diffractive optics, or optical phase arrays, built directly into the silicon.
Meaning they try to focus the light using the flat chip itself, right? Without adding all those external bulky mirrors.
Yes, exactly. The advantage is that this approach is incredibly scalable. You can print millions of these on a single wafer using standard manufacturing.
So what's the catch?
The downside is severe. Because you are trying to bend and focus light using flat, two-dimensional structures, the beam quality is heavily diffraction degraded.
So it's blurry.
Very blurry. The light you project into the room spreads out way too much. You lose the crisp, high-resolution focus you need for any kind of precise real-world application.
Okay, so option A is highly scalable, but you get a blurry mess. What was option B?
Option B was micromechanical scanners. Think of tiny glass fibers that physically sweep back and forth, or microscopic mirrors known as MEMS mirrors.
MEMS.
It stands for microelectromechanical systems. Now, these give you a gorgeous, sharp, single-mode beam of light.
Because it's an actual physical mirror?
Right, because they physically tilt a reflective surface, they can steer the beam with incredible precision. But they introduce a new set of physical limits. They are what we call inertially limited.
Let's pause on that. Inertially limited, you mean because the mirror physically weighs something, moving it back and forth takes a lot of effort?
It takes effort, and it takes time. I mean, even a microscopic mirror has mass. If you want to steer a laser beam quickly enough to draw a high-resolution image in the air, that mirror has to oscillate incredibly fast.
Like thousands of times a second.
Exactly.
Oh.
And to double the speed of a physical object reversing direction, you need a massive increase in energy. Eventually, you hit a limit where the mirror simply cannot move any faster without requiring so much power that it literally melts.
Oh, wow.
Or the physical hinges just snap from the stress. Plus, because they are separate physical components, they are nearly impossible to seamlessly integrate onto a flat microscopic chip. They sit off to the side, taking up variable space.
So it's like trying to paint a microscopic masterpiece, but you only have two choices. A brush that is too heavy to lift, or a lightweight brush that splatters paint everywhere.
That is a great way to put it. You want the precision of the heavy brush with the agility and flatness of the splatter brush.
Well, wait, I have to push back on this. If the MEMS mirrors the sharp ones are just too heavy, why couldn't they just make the mirrors smaller?
Shrink the mirror, lower the mass.
Yeah, solve the inertia problem, right?
You would think so. But here is where the physics of light fights back again. It comes down to something called pupil plane resolution.
Which means what, exactly?
It is the relationship between the physical size of a mirror and its ability to keep a beam of light tightly focused over a distance.
Okay.
If you shrink a mirror down to make it lighter and faster, the reflective surface becomes so small that diffraction takes over again.
Oh, so the light spreads out anyway?
Precisely. The mirror can no longer hold the beam together, and the light becomes blurry. You hit an absolute physical brick wall. Decrease the size to get speed, you lose the resolution.
And if you increase the size to get the resolution back, they become too heavy to move fast.
Exactly. For years, there was no way around it using that traditional geometry.
So how did scientists figure this out? Because clearly, if we are doing a deep dive on this, someone cracked the code. This is where the story gets really fascinating.
Well, because shrinking the old mirrors didn't work, a group of scientists realized they had to completely reinvent the physical geometry of how light escapes a chip.
They needed a totally new approach.
Right. They stopped trying to improve the flawed mirror design and instead figured out how to bridge that mismatch between the flat, guided tunnels of the chip and the open 3D space of the room.
And that brings us to the breakthrough. We're looking at a landmark paper published on March 11th, 2026 in the journal Nature.
And the team behind this is a real powerhouse.
Absolutely. We are talking about researchers Matt Saha, Y. Henry Wen, Andrew S. Greenspan, Matthew Zimmerman, and their colleagues. And they represent an incredible lineup of institutions. MIT, the Miter Corporation, Axiomatic AI, Sandia National Laboratories, the University of Colorado, and the University of Arizona.
It is a massive collaboration across multiple disciplines. And what they invented to solve this problem is genuinely a marvel of nanoengineering. They call it the photonic ski jump.
The photonic ski jump. I mean, when you look at the scanning electron microscope images provided in the paper, it literally looks like a microscopic Olympic ski jump.
It really does.
It starts totally flat on the silicon chip, and then it curls up, lifting right out of the chip into the air at a perfect 90-degree angle.
Mechanically speaking, it is a nanoscale waveguide that is monolithically integrated on a piezoelectric microcantilever.
Okay, let's translate that for everyone. Monolithically integrated means it is built directly out of the exact same block of silicon, right? No separate parts glued together.
Correct. It is etched directly out of the chip itself.
And the second part, the piezoelectric microcantilever. A cantilever is like a diving board attached at one end.
Right.
But piezoelectric, meaning the material physically reacts to electricity. You zap it and it twitches or bends.
That is the core mechanism.
Mm-hmm.
You actually see piezoelectric materials in everyday life, like the crystal in a push-button lighter that creates a spark when you hit it.
Oh,
But here they are doing the reverse. They are applying tiny electrical currents to make the material physically bend. But the first challenge wasn't just making it twitch. The challenge was getting a flat piece of glass and silicon to permanently curl up into that ski jump shape.
right, because silicon chips are rigid and flat. How do you get a microscopic piece of material to just naturally bend upward at a 90-degree angle without snapping in half?
To understand the curl, you have to realize how incredibly thin this diving board is. The entire structure is only about 2 micrometers thick.
Wow.
That is a tiny fraction of the width of a human hair. To get it to curl, they used a bimorph structure. That means they layered thin films of different materials on top of each other.
Okay, different materials.
And these materials have built-in stress from the manufacturing process. The bottom layers naturally want to expand, and the top layers want to compress.
Hold on, I am trying to picture this. If it is a structural tug of war with the bottom pushing and the top pulling, why doesn't it just crumple like a potato chip? How do they get a perfect, smooth half pipe?
That is the genius of it. If they just let the stress release naturally, it absolutely would warp or curl sideways unpredictably. So they introduced a brilliant technique. They etched what they call a cross-rib pattern into the top layer of silicon dioxide.
Rib pattern.
Imagine taking a piece of paper that you want to roll into a tight tube. If you just squish it, it folds randomly. But if you take a pen and score parallel horizontal lines across it, it will naturally roll up perfectly along those lines.
Ah, so the horizontal grooves force the tension to release in one specific direction, driving that longitudinal curl straight up into the air.
Precisely. The cross ribs guide the stress. So now you have a curling diving board with a microscopic light tunnel running right up the middle of it, shooting light straight up off the chip.
But a static ski jump isn't enough, right? To be useful, to draw images or steer lasers, it has to move.
And this is where the piezoelectric part comes in. They run electricity to it. And we are talking standard CMOS level voltages, the exact same low voltage electricity that is running through your laptop or your phone right now.
And because this diving board has a submicrogram mass, meaning it weighs virtually nothing, it doesn't suffer from the inertia problems of those old clunky MEMS mirrors.
Exactly. When they apply an alternating voltage, the piezoelectric material forces the tip of the ski jump to flutter. It vibrates at kilohertz rates, thousands of times per second.
Wait, if I have a microscopic 2 micrometer thick piece of glass in silicon vibrating thousands of times a second, how does it not instantly shatter into a million pieces? It sounds incredibly fragile.
That was the massive question hanging over this research. Is it durable?
Yeah?
The team put it through rigorous testing. They forced it to vibrate continuously, monitoring it for material fatigue. It survived over 1 billion cycles without breaking, degrading, or losing its optical properties.
1 billion cycles? That is insane.
And it achieves this because it has a mechanical resonance quality factor of over 10,000.
Meaning what in real-world terms?
Meaning it moves incredibly efficiently. If you struck a tuning fork with a quality factor of 10,000, it would ring pure and clear for a remarkably long time without losing energy to internal friction or heat.
Oh, I see.
The ski jump flexes perfectly with its own natural resonance. Because it isn't fighting internal friction, it doesn't heat up and it doesn't snap.
Which brings us to the actual performance. The number from the paper that just blew my mind was the spot rate. How many distinct, focused points of light this thing can project in a given time. They achieved a footprint-adjusted spot rate of 68.6 million spots per second per square millimeter.
What's fascinating here is putting that number into context. When we compare it to those two bad options we discussed at the start, the blurry diffractive chips and the heavy MEMS mirrors, this new ski jump is more than a 50-fold improvement over the absolute best state-of-the-art MEMS mirrors.
50-fold.
And it is a 1,000-fold improvement over those scanning fiber devices.
1,000 times better, and the power consumption is absurdly low. The direct current hold power, the energy needed to just hold the ski jump in a bent position, is just 10 nanowatts. That is functionally zero power.
It is remarkably efficient, and here is how they actually use it to draw. The researchers designed the cantilever so they can drive the left and the right sides of the base independently.
Okay.
By applying slightly different frequencies to each side, they make the tip of the ski jump wobble in 2 dimensions side to side and up and down simultaneously.
Like a high-speed microscopic spirograph.
Yes. The tip traces out these rapid, complex mathematical paths called Lissajous curves. And as the tip is flying through these loops thousands of times a second, they pulse the laser light coming out of it on and off.
So they are painting pixels in the air.
By synchronizing the laser pulses to the exact position of the vibrating tip, they can draw shapes. In the paper, there are actual photographs where they use this microscopic diving board to project full-color videos.
That is wild.
They spelled out the letters QMP, which stands for the Quantum Moonshot Project, alongside the logos of MIT, Mitari, Sandia, and Arizona. Perfectly crisp, high-resolution images projected directly from a flat chip.
But here's where it gets really interesting. Projecting logos is a great proof of concept. But they took this tiny, vibrating, curling piece of silicon, put it into a vacuum chamber, and dropped the temperature down to a freezing 6.9 Kelvin.
Deep space temperatures, near absolute zero.
Right, and they do this because they wanted to see if the beam was stable enough and precise enough to control individual quantum bits. They shot the light from the vibrating ski jump directly at something called silicon vacancy centers inside diamond crystals.
Now, to clarify how difficult this is, a silicon vacancy center is a specific kind of microscopic flaw in a diamond lattice where 2 carbon atoms are missing and a single silicon atom sits between them.
Like a tiny imperfection.
Yes, and it acts as an artificial atom. It is one of the leading candidates for acting as a qubit, the fundamental building block of a quantum computer. To talk to a qubit, to write data to it, or read data from it, you need a laser beam of a very specific color that is perfectly stable and aimed with nanometer precision.
Because it's so small.
Right. If the beam wobbles even a fraction of a hair's width, the qubit ignores it entirely.
And the ski jump pulled it off.
It did. The fact that the ski jump could initialize and read out single photons from these microscopic diamond defects while sitting in a freezing vacuum while vibrating at kilohertz speeds.
It proves this isn't just a flashy projector, it is an ultra-precise quantum control tool.
Exactly.
So we have a microscopic, ultra-fast curling diving board that shoots perfect beams of light, survives a billion cycles, draws almost no power, and can literally talk to individual quantum atoms in a freezing vacuum.
Which brings us to the big question. Why does this matter to you listening to this deep dive right now? Well, if we step back and look at the whole digital landscape, our electronics are becoming incredibly intelligent. But they are trapped. This tiny optical pipeline fundamentally upgrades what we call the digital intelligence value chain.
How so?
It gives our computers eyes and hands that operate at the speed of light, directly bridging the chip to the physical world without the old physical bottlenecks.
It's like we are currently choking on the immense data streams of the 3D physical world. The world has so much physical detail, and our chips just can't get the data in and out fast enough using old, clunky mirrors. This discovery is essentially upgrading the physical universe's internet connection to our computers, moving us from a dial-up modem to blazing fast fiber optics. Let's look at how this changes specific technologies. Take augmented reality, for instance.
AR is a perfect example of the chip-to-world bottleneck.
Yeah.
Right now, AR headsets look like you have strapped a heavy toaster to your face.
Right, they're huge.
And that is entirely because of the optics. They're trying to fit bulky lenses and heavy MEMS mirrors near your eye to project an image wide enough for you to see.
And the ski jump changes the architecture entirely.
It allows for truly solid-state near-eye displays. Because the ski jump is so small, you could fit thousands of them on a chip the size of a grain of rice. You can embed the projector directly into the frame of normal-looking glasses.
Just everyday glasses.
The ski jumps can project millions of pixels a second directly onto your retina. It paves the way for AR glasses that are indistinguishable from your daily sunglasses.
And what about LiDAR? Self-driving cars currently rely on those spinning mechanical buckets on the roof, firing lasers to map the 3D world. They are expensive, they have moving parts that break, and they are aerodynamically terrible.
The ski jump allows you to replace that spinning bucket with a flat, solid-state chip. You could have incredibly compact, high-resolution LiDAR systems hidden seamlessly in the headlights or the trim of a car, sweeping the road with lasers millions of times a second with zero macro-scale moving parts.
But I want to circle back to the quantum computing aspect, because that seems like the most profound shift. We always hear that quantum computers are going to revolutionize medicine, cryptography, and artificial intelligence. But there's a wiring problem.
A massive wiring problem. The holy grail right now is building a fault-tolerant quantum computer. But to do that, you don't just need 10 or 20 qubits. You need to control millions of physical qubits simultaneously.
Wow, millions!
Under the old system, if you have to wire up a separate, bulky fiber optic cable and a mechanical mirror for every single qubit, your quantum computer quickly becomes the size of a football stadium. It becomes physically impossible to keep the entire system at absolute zero.
Just doesn't scale.
It doesn't scale at all. But the ski jump fundamentally solves the scaling issue. Because it is made out of silicon and silicon dioxide, it can be mass-produced in a standard 200-millimeter CMOS foundry.
Wait, the exact same factories that print the chips for our smartphones?
Yes.
So you could print a grid of 1,000,000 ski jumps on a single wafer?
Exactly. You can lay out a massive grid of these tiny curling diving boards on a single chip, place it directly above your quantum processor, and have it act as a massive optical traffic controller.
That is incredible.
It can shoot millions of individual light beams directly to millions of qubits simultaneously, all inside the same microscopic cryogenic chamber. It completely changes the architecture and the timeline for building a scalable quantum computer.
So to summarize the incredible journey we have been on today, we started with the frustrating physical limits of clunky MEMS mirrors and blurry diffractive chips. A world where engineers were trapped behind an inertial brick wall, forced to choose between being precise or being scalable.
Right.
And we ended with the brilliant invention of a nanoscale ski jump, a device that uses built-in bimorph stress and cross-rib patterns to literally curl 90 degrees out of the silicon. It projects nearly 70 million perfect points of light per second, vibrating thousands of times a second without breaking, and controlling everything from the pixels in an AR display to the foundational atoms of a quantum computer.
If we connect this to the bigger picture, this is a beautiful reminder of how true scientific leaps actually happen. They rarely happen by just incrementally improving a flawed existing design. Making a bad, heavy mirror slightly smaller wasn't the answer.
Right, it was a dead end.
The breakthrough happened when these scientists stopped trying to fight the flat 2D limits of the microchip and literally looked at the problem from an entirely new dimension. By manipulating internal material stress, they bent the chip itself up into the 3D world.
Bending the rules of the chip to fit the real world. So what does this all mean? I want to leave you with this final thought to mull over. We started by imagining those perfect sci-fi holograms, that seamless blend of the digital data and the physical room. If a microscopic curling diving board is what it takes to open a high-speed optical pipeline between a computer chip and the physical world, what other invisible digital barriers are just waiting for the right nanoscale geometry to bridge them?
It makes you wonder.
If this discovery is just the beginning, what might scientists uncover next? Thank you for joining us in the Deep Dive Lab today. If you enjoyed this journey into the bleeding edge of science, be sure to follow and subscribe for more stories that decode the future, one paper at a time. Until next time, keep your curiosity dialed up.